Torch, where. Description. The torch, where function is a p-torch operation that returns a tensor of elements selected. According to a condition, it is analogous to the if statement in traditional programming languages, allowing you to perform conditional element selection within tensors. Inputs. Condition a Boolean tensor D-type torch, bool where true values indicate elements to be selected from the X tensor, and false values indicate elements to be selected from the Y tensor. X a tensor containing the elements to be selected if the corresponding element in the condition tensor is true. Y a tensor containing the elements to be selected if the corresponding element in the condition tensor is false. Outputs. Output a tensor with the same shape as the condition tensor, containing elements from either the X or Y tensor based on the condition. Steps. For each element in the condition tensor, if the element is true, select the corresponding element from the X tensor. If the element is false, select the corresponding element from the Y tensor. Challenges and fixes. Challenge 1. Ensuring that the shapes of the condition X and Y tensors are broadcastable. Sample use case that resulted in challenge 1 trying to apply torch, where with tensors of incompatible shapes, resulting in a runtime error. Fixes to challenge 1. Use torch, broadcast shapes to check for broadcast compatibility before calling torch, where, if necessary, reshape or expand the tensors using torch, reshape, torch, view, or torch, and squeeze to ensure broadcast compatibility. Challenge 2. Handling cases where the X and Y tensors have different data types. Sample use case that resulted in challenge 2 using torch, where with a condition tensor of D type. Torch, bool and X and Y tensors with different data types, e.g. torch, float 32 and torch.int 64. Leading to unexpected type conversion issues. Fixes to challenge 2. Ensure that the X and Y tensors have the same data type before calling torch, where, if necessary, convert one of the tensors to the desired data type using torch, float, torch, long, or other appropriate type conversion functions. Challenge 3. Handling cases where the X and Y tensors are not defined or are empty. Sample use case that resulted in challenge 3 attempting to use torch, where with X or Y being none, or an empty tensor, causing a runtime error or producing unexpected results. Fixes to challenge 3. Before calling torch, where, explicitly check if X and Y are defined and not empty. If they are not, provide default values or handle the situation appropriately to prevent errors. Challenge 4. Handling cases where the condition tensor contains nans not a number. Sample use case that resulted in challenge 4 using torch, where with a condition tensor containing nans, leading to unexpected behavior or errors. Fixes to challenge 4. Before calling torch, where, use torch, ISNA to identify and handle nans in the condition tensor. You might need to replace nans with false or other appropriate values to ensure consistent behavior. Torch generator. Description. A torch generator object in ptorch is responsible for managing the random number generation process. It encapsulates the state and settings that determine how random numbers are produced, allowing for control over the reproducibility of your results. Inputs. None. Torch generator doesn't directly take any input arguments during its instantiation. Outputs. Random numbers. It provides methods to generate random numbers, e.g. torch, randint, torch, randn, which are then used in various ptorch operations. Steps. Initialization. You create a torch generator instance using torch generator. Setting seeds. You can control the randomness by setting a specific seed using the manual seed method. This ensures that the same sequence of random numbers is generated each time you run your code with the same seed. Generating random numbers. You utilize methods like torch, randint, torch, randn, etc. in conjunction with the generator to produce random numbers within your desired ranges and distributions. Challenges and fixes. Challenge 1. Non-deterministic randomness. If you don't set a specific seed, your code might produce different random numbers each time you run it, making debugging and reproducibility difficult. Sample use case that resulted in challenge 1. Training a neural network with random initialization weights but not setting a seed might lead to varying results across different runs. Fixes to challenge 1. Use torch, manual seed before any random number generation to ensure consistent random number generation across multiple runs. Challenge 2. Incorrect seed usage. Setting a seed at the wrong place in your code might not give you the desired deterministic behavior. Sample use case that resulted in challenge 2. Setting the seed after some random number generation has already occurred might not achieve the intended reproducibility. Fixes to challenge 2. Ensure you set the seed before any random operations in your code. If you are using multiple GPUs, you might need to set seeds for each device separately. Challenge 3. Multiple generators. Using multiple torch generator instances might lead to unpredictable behavior unless they are carefully managed. Sample use case that resulted in challenge 3. Using one generator for model initialization and another for data augmentation could cause unintended interactions between random number sequences. Fixes to challenge 3. For consistent random number generation across different parts of your code, ideally use a single torch generator instance and pass it as an argument to all functions that need to generate random numbers. YAML. Torch initial seed. Description. The torch initial seed function in ptorch sets the initial seed for the random number generator RNG. This allows you to control the starting point of the RNG, which in turn influences the sequence of random numbers generated in subsequent operations. This can be crucial for reproducibility, especially when training machine learning models. Inputs. Seed and integer representing the initial seed value. This value is used to initialize the RNG state. Outputs. None. The function does not return any value. It directly modifies the internal state of the RNG. Steps. Setting the seed. When you call torch initial seed. The specified seed value is used to initialize the state of the RNG. Generating random numbers after setting the seed. Any subsequent calls to functions like torch, rand, torch, randint, or torch, randn will generate random numbers based on this initial seed. Challenges and fixes. Challenge 1. Unpredictable results. If you don't set an initial seed, your random numbers will be generated based on the system's current time. This can lead to inconsistent results if you run your code multiple times or on different machines. Sample use case that resulted in challenge 1. Training a neural network without setting a seed can produce different model performance every time you run the training. Fixes to challenge 1. Use torch initial seed to set a specific seed before training or any operation that relies on random numbers. Challenge 2. Different behavior across devices even with the same seed. If you run your code on different devices like CPUs or GPUs or across different runs of your code on the same device, the generated random numbers might differ due to subtle variations in hardware or software. Sample use case that resulted in challenge 2. A model trained on one machine might perform differently when deployed on another machine, even with the same seed. Fixes to challenge 2. Use torch, manual seed to set the seed for both CPU and CUDA GPU devices. Use a deterministic backend for ptorch if possible to ensure consistent behavior. YAML. Torch getRing state. Description. The torch getRing state function retrieves the current state of the ptorch random number generator. RNG. This state encapsulates the internal parameters used by the RNG to generate pseudo-random numbers. Inputs. None. Outputs. Current RNG state. A torch byte tensor containing the current state of the ptorch random number generator. This state can be used to restore the RNG to its previous state at a later point. Steps. The function reads the internal parameters of the ptorch RNG, which determine the sequence of random numbers generated. It encapsulates these parameters into a torch byte tensor object. Challenges and fixes. Challenge 1. Misunderstanding the scope of the RNG state. Sample use case that resulted in challenge 1. A user might assume that torch getRing state captures the state of all random number generators in the application, but it only captures the state of the global ptorch. Fixes to challenge 1. Understand that torch getRing state specifically retrieves the state of the global ptorch RNG. To manage the states of other random number generators, e.g., those used within libraries or for specific tasks, you might need to consult the documentation of those libraries or use additional mechanisms for state management. Challenge 2. Incorrectly using the retrieved state. Sample use case that resulted in challenge 2. A user might attempt to directly manipulate the returned torch byte tensor to change the RNG state without using the appropriate functions. Torch getRing state. Fixes to challenge 2. Always use torch getRing state to restore a previously retrieved RNG state. Directly modifying the torch byte tensor can lead to unpredictable behavior and may not produce the desired results. Torch getRing state. Description. The torch getRing state function sets the state of the random number generator RNG for ptorch. This function is crucial when you want to reproducibility ensure your results are consistent across multiple runs of the same code. By setting the RNG state to a specific value, you guarantee the same sequence of random numbers, resulting in identical outcomes. Debugging. Identify issues related to randomness by controlling the random number generation process. Research and experimentation. Explore different random number sequences to evaluate the impact on your model's performance. Inputs. State A1D torch byte tensor representing the state of the RNG. This tensor holds the internal state of the random number generator, which is responsible for producing random numbers. Outputs. None. The function modifies the global RNG state in place, making the change persistent. Steps. The provided state tensor is used to reset the RNG state. This means the random number generator starts generating numbers from the point defined by the state. The function operates on the global RNG, affecting all future random number generations within the ptorch environment. Challenges and fixes. Challenge 1. Inconsistent results due to uninitialized RNG. If the RNG is not initialized with a specific state, each run might produce different results due to the random nature of the generation process. Sample use case that resulted in challenge 1. You run a deep learning training loop multiple times, and the model's performance varies significantly across runs. Fixes to challenge 1. Initialize the RNG using torch, manual seed or torch, manual seed all before starting the training loop. This guarantees a fixed starting point for random number generation, ensuring consistent results across different runs. Use torch, string state with a specific state tensor to control the random number generation. Process precisely. Challenge 2. Inability to replicate results in different environments if the RNG state is not preserved across different environments, e.g., different machines, different PTorch versions. You might encounter discrepancies in the results. Sample use case that resulted in challenge 2. You train a model on one machine and try to replicate the training process on another machine, but the results deviate considerably. Fixes to challenge 2. Save the RNG state using torch, getRing state and load it back using torch, string state. This ensures the same sequence of random numbers is used on different systems. Consider using a deterministic pseudo-random number generator for increased reproducibility across different environments.